Well, good morning. Bill Ragsdale here for the Silicon Valley Fourth Interest Group. This is by electrical transcription. I wish I could be there in person, but I am enjoying the piney woods at Yosemite right now. Today we're going to discuss a two-dimensional data structure implemented in Forth. This is our common matrices that most of us are familiar with. Forth, as we know, has a variety of data structures, but they exist for the internal operation of Forth and don't lend themselves to a lot of the applications. Those data structures are first as a byte or character, a word, a cell, a float number, an array, or files themselves. The general need for data structures would include a database, matrices, vector graphics, bit graphics, sound, video, AI structures, and simulation structures, and probably some more that you can think of. Well, my need was fairly straightforward. I wanted to do math analysis and statistical analysis. I currently use MATLAB and R, but I wanted to be able to do my work in Forth, and I was doing some rather interesting processing that Forth would seem to do the best. I wanted to be able to load data from CSV files, to save results into CSV files, to set the data size anywhere from 1 byte to 8 bytes for anywhere from cells for characters to floats. Presently, I'm just using floats and characters, but I expect that may expand in the future. I've adopted the notation from Scientific Forth by Dr. Julian Noble. He wrote a great book on scientific analysis, but it's quite out of date, and a number of the structures and memory usage don't lend themselves to our current usage. So what can my structure do? Well, first, I can load literal values into matrices. I can load a matrix with random numbers. I can read and write data files. I can do a formatted print, do math on matrix, row, column, subarea, and cell. I can copy and move between rows, columns, subareas, and cells, do a multi-column sort, linear algebra that we're familiar with, transpose, matrix multiply, equation solution, inversion, Gaussian elimination, and so on. And finally, a limited amount of alphabetic processing, primarily for labeling reports. Here's a quick demonstration. First, I'm going to create a matrix with 1 for create X. That is 1 row, 4 columns, and the X ends with a left brace, which is my convention for a matrix declaration. We simply take X brace and then the 1, 2, 3, 4, and that is the sequence to load 4 values into X. And then X list shows those values in green at the right, 1, 2, 3, 4. Things that can be done with this once it's in this form. At the bottom we see an X4, 4 resize, so it will take the 1 by 4 matrix and resize it to be 4 by 4. Transpose will transpose rows and columns, and finally list to list it. And we see the result. At the bottom right, in green, we see the 1, 2, 3, 4, which was our original row, transposed now into a column. And in blue, we see all of the values that were filled in by the resize. Here are the components. First, we have the data area that holds our information. It is row by column by cell size in bytes. We have a descriptor. The descriptor holds the cell size, the number of rows, the number of columns, and then a number of control parameters, which we'll see in just a moment. There's a fourth name for each matrix, and there are words to access the matrices by the entire matrix, by single cells, and by the rows and combinations. Here are the conventions that I've adopted. First is that matrices are referred to by the address of the first byte of their data area. That is the data area, rows, columns by cells. First byte gives us how to locate that data area. Then the descriptors are located by a negative offset in front of that data area. So there are 8 cells reserved and used in front of the data area. I'll note in this case that rows and column numbers run from 0 to r-1. This is a little different than the normal matrix operations, which normally go from 1 to the number of rows, but 0-based addressing lends itself much better to Forth. The convention that I have for matrix names, as I said, is X with the left brace. So every matrix name ends with the left brace, and you'll see how it blends into the syntax in a very clear way. The next row says X with a right brace action. So the right brace signifies an action on a full matrix. The bottom row says then X, R1, C1, negate, and this operates just on one cell. With the double brace in there, it signifies we're operating on a single cell, indicated by its row and column number. Here's a look at the descriptor. The descriptor is the heart of the programming in this case. First, there is a pointer to the name's parameter field address. The matrices are doubly linked. There is a pointer from the matrix name into the data area, and there's a pointer backwards to the PFA of the name. There is a backlink, so if a matrix is resized, they actually form a linked list, and it's possible to go forward and backward on that list, and if you resize the matrix, you can reclaim it by moving backwards. There's a pointer to the data area. It's primarily used for a security check or an error check. And then come the integer values for the cell size, the number of columns, and the number of rows. So we see 6 parameters. As an example, I've created an 8x5 matrix X, and then the word descriptors prints out what the descriptor looks like. First, we see its memory address in hex. Then we see the parameter field address, also in hex. Then the backlink, which presently is 0. The check digit, which is the hex address of the data area. The size is the cell size 8 for floats. And then the parameters of 5 and 3, which is rows and columns. Here is the design shown graphically. The top green, we have X followed by the parameter field, and that holds the pointer to the data area. The data area is in the square box at the right, and we see that its size is 8 by 5 by 3 bytes. The parameter field comes before it. That's on the lower left. The PFA points back to the parameter field. The link currently is 0. The check value points forward to the data area, and then we see the values of 8, 5, and 3, which is the field size, the number of columns, and number of rows. So let's see the magic. The heavy lifting in this case is done by a word double right brace. The syntax for usage would be to say specify a matrix name X, a row number, a column number, and the double right brace. The double right brace then calculates the storage area for that particular cell. So by that sequence, we can address any cell in the matrix, and then by combinations of rows and columns, we can manipulate rows, columns, and the entire matrix itself. The definition of the double right brace is simply swap to pick the number of columns times over size times plus. And that sequence extracts the cell size from the input parameters. Notice the input syntax is very simple and clear, and as I said, the heavy lifting is done by that double right brace. So let's see how we access a cell. First, we're going to create a matrix, 3 rows, 4 columns, create the matrix X. Then X integers fills it full of integers, 0 through 11, and then X lists them out, and in red we see the full matrix. Second row from the bottom, we are now going to access one cell. So the X11 double right brace, fetch, floating fetch gets the value, F prints it out, and below we see 5 dots. So we have reached into that matrix, into the cell at the 1 column row, and print it out. Here's an example of some row-wise arithmetic. We'll create a matrix 4 by 3 named X. Then the next line down says says X1 7E R number sign fill. This puts the number 7 in the row number 1. X2 2E R fill goes into row 2. X1 2 3 does a summation. It takes this matrix, adds it to itself, and puts it by row-wise. It takes row 1 of this matrix, takes row 2 of the matrix, takes row 3 of the matrix, adds the first 2 rows together, and puts them in row 3. And we see the result there is 9. The second row is all 7s, third row is all 2s, and the third row is all 9s, which is the row-wise summation. And then of course, lists out the entire result. I've developed quite a rich number of matrix operators. We can create a full matrix, floating point matrix, or the create star will create a matrix of any size. I mean, any size. You can have a matrix of 1 cell size to a matrix of 1,000 cell size. List and sublist will list the entire matrix or any portion of it. Copy, rcopy, ccopy, subcopy, all give us variations to go from matrix to matrix with a copy. We then have operators to clear, fill with integers, fill with random numbers, to resize, to handle dimensioning. Dimensions gives us the row and column size. Rows, columns, cells, and bytes let us access particular parts of the matrix. And finally, the more complicated words, determinant, transpose, invert, and bubble. We'll see bubble in just a moment. Here are the math operators. There are 32 math operators in all. They are add, subtract, cell-wise multiply, and cell-wise divide. There are separate operators for matrix multiply and divide. So these are cell-wise operations. The different types are that we can do a matrix, we can do an arithmetic on an entire matrix, we can do it on a common row, we can do independent rows, common column, independent columns, single cell, common subcell, and independent subcell. So any way you want to address a matrix, there is a word to do it. As an aside, in most matrix languages, this is done by the syntax, which is a combination of square brackets, braces, curly braces, parentheses, colons, and words like begin, end. Instead of having that fairly complex syntax, I have an extremely simple syntax, very straightforward, and the variety of addressing is done in the operator. An amazing part is that with factoring, every one of these words factors down to a single word, which is right paren, left brace, sub x, right paren. The x represents the math operation. So you specify a submatrix or the entire matrix, a math operation, pass it to that one word, and the entire operation takes place. And these are done over 3 matrices. You have a matrix 1, matrix 2, and matrix 3. For example, you add the first 2 matrices together and put into the third. And here's a simple example of alphanumerics. I've created a matrix. 1, 3, 15 says give a cell size of 1. We want 3 rows, 15 columns, and it is named alpha. Then the second line is alpha and alpha fill. So this takes the matrix, whatever it is, however it is, and fills it full of alphabetic characters. Primarily this is done for testing. Then alpha character list prints it out, and we see the matrix has been printed out from ASCII A at the start, ending down to an ASCII lowercase m at the end. Total of 45 characters. So let's look within a definition, see how it works. We create a matrix, again, in this case, integers from 1 to 14. We transpose it, and there is the transposed matrix. Again, normal programming would be quite involved. This matrix language takes it all down to a single one-line operation. Here's how that word actually operates, the transpose works. The first line, which is a question X and then dimensioning, opens up a transient matrix that only exists for the duration of this one word. We go out and grab memory at high memory, create a matrix, use it for transient purposes, and then forget it. We then, on the second line, we dupe transient copy. We copy the input matrix to the transient. We then set up the loop dimensions, and then with the zero do, dupe, zero do, and in green we see that we address the transient matrix, we address at the row and column y, x, I, and j, and fetch a single character. Then we go to the the input matrix, which is unchanged, and then reverse the two indices to ji and then store. So we're processing from the transient copy of the matrix back to the original. At the very end then, we drop our control parameters and we close transient, and our original input has the transposed output. So let's do one final fairly elaborate example. First, we're going to generate a set of random data. So I declare a matrix with 16 rows and 1 column. Then I fill it with random integers. And in this case, the random integers are between 0 and 10. And they have their integers because in their specification, you see a 10E, 0E. 10E is the range of random numbers from 0 to 10, and the 0E says 0 decimal places. Then we create another matrix, and this one is 16 by 2, and we fill it with random floats. In this case, they're filled with random floats from 100, and they have 1 decimal place. Now I copy the integers from matrix to another. So this is doing a C column. You see where it says ref x0 C copy. This is copying from the reference matrix to the X matrix, the 0 column. And finally, we list the composite. So on the right, you can see our result. In the first column, we have random numbers as integers that are ranged from 0 to 10. In the second column, we have random numbers, integers, fractional numbers 0 to 100. Now we do some work on that data. Let's do a sort. So in green in the center, we say x1 bubble. This is doing a bubble sort on the column 1. Then we go x0 bubble, does a bubble sort on the 0 column, and then list. Over on the right-hand side, we see that on the left-hand side, there are 6 0 values, and the subsort on those run from 4.6 down to 96.2. There was a single value under 1. There were 2 values under the subsort of 2, 9.6 and 16.7. Same with 2 values under 5, and 7 and 8 and 9 have subvalues that are unique. Don't turn your nose up at a subsort. In this case, it takes n squared plus n over 2 comparisons, which can be a large number. I did a test example for this of creating a matrix of 100 rows, 1,000, 5,000, and 10,000. The 100-row sort takes 16 milliseconds. The 1,000-row sort takes 1.9 seconds. The 5,000-row sort takes 31 seconds. Then it gets to be a pretty large number. 10,000-row sort takes 1 minute 58 seconds. I believe I did an estimate on a 1,000,000-row sort, and I believe it took 6 days. So the bubble sort is very simple, very basic, easy to program, and for most applications should be sufficient. I'll point out that if you take a 10,000-row matrix and fill it full of daily data, that data can exist over 27 years. So in 2 minutes, you can do a data sort on 2 years' worth of data. So the benefits. Well, first, we have a very flexible data structure. We can have any number of rows and columns and any cell size within those matrices within the limits of memory. A very rich suite of support words, and being fourth, if you need a word that you don't find, you take something that's similar and modify it. And finally, I'd like to point you out to my Win32 Fourth guide on GitHub, because it explains in great detail about 80 pages of everything I've discovered on Win32 Fourth. So the future work, I'm presently involved now in adding file support and adding virtual memory, heap memory from Windows, adding words for statistical support. I may be adding an expansion on text entries and some other number types, for example, complex numbers, and to expand the report generation features. So as to wind up, I'd like to thank and credit Andrew McEwen and Tom Zimmer, who created Win32 Fourth. It is a stable system. It was expanded and brought up to date by a European team in the early 2000s, and I appreciate their work greatly. And finally, I'd like to thank Dr. Julian Noble, the late Dr. Julian Noble, the creator of this notation, and in his book, Scientific Fourth. For references on this, go to my section at GitHub. It's Bill Ragsdale at GitHub on Fourth Projects, and my Win32 Fourth guide is there. So thank you very much. Pleasure to be with you today. I may be able to join in on a few little comments if I can get to the internet on Saturday. But back to Kevin, and thank you all for your kind attention.